All right, so let's create the vesting DApp. We're going to be using the npx create Solana DApp scaffold because it connects both a front end and a back end in one workspace and makes it a lot easier when you're making a full decentralized application. So let's get started by setting up the scaffold. We're going to navigate to our terminal and just type in npx create Solana DApp. And now we're going to enter the project name. We'll do token vesting. We'll select the preset for Next.js, Tailwind, and then the Anchor counter program. And this is creating a new workspace with NPM. So it's going to take a second to load. We'll wait for everything to generate, and then we're going to open this workspace in VS Code and get started. Okay, so this creates a new folder inside the directory that you ran the command. So we're just going to cd into that folder. And then we're going to open in VS Code. Okay. And just to get everyone familiar with this scaffold, how it sets up the workspace for you, you have your web folder that has everything for the front end of the application. And you can see the app, the components, and all of the needed configurations. We're going to work with this later. So we're going to start out with our Anchor smart contract. So in the Anchor folder, you can see it has everything set up for the back end of the application. We have our programs, and then you go into source, and this is where the main smart contract lives in your librs. Now, we also have a few other folders generated that we're going to use later on in this application. But let's just first start with our librs. So you can see this is just a basic counter that was generated. If you actually run this with npm run dev, it's going to actually show the front end and a working counter. But we're going to change all of this for our vesting contract. So what we can do is just delete everything within the program. As you now know, by working through the bootcamp, this program macro defines all of the instructions for your smart contracts, and then you have the corresponding data structures for all of your context. So we're just going to delete everything related to the counter and just have the basic setup for an Anchor smart contract. So that's using the anchor-lang import. It has your declare ID with your program ID of the smart contract. And then this is where all of your instructions are going to live. Now, what we need to do is rename everything from counter over to vesting. So let's start by updating the name of this program to vesting. And then we're going to navigate into our cargo file. So the package name is counter still, so we'll update this to vesting. Okay. And then let's see, we're just going to Command-Shift-F and see everywhere else that counter is written. And we just want to update that. So it's going to be in quite a few places. This will take just a second. Anything related to the TypeScript files for our web app, we're just going to deal with later when we start working on the front end. So all of this we can just ignore for now. So now we have to set up our cargo TOML for this program. And in our vesting contract, we're going to be moving SPL tokens around, as well as using a Solana program. So we're going to update our dependencies in our cargo TOML to use both of those crates. So we can just open up our terminal and run cargo add. And we're going to add first our Anchor SPL. Sorry, we actually need to navigate into our Anchor directory. So one thing to note whenever you're using the Create Solana DApp scaffold is everything related to the Anchor smart contract lives in the Anchor folder. So whenever you're running Anchor commands or any of your cargo commands, it has to be done in the Anchor folder. So we'll cd into Anchor, and now we can run cargo add Anchor SPL. Okay, so you can see our dependency updated with Anchor SPL. And now if you're following along, depending on the time that you're following along, this might have a different version. So if you want to make sure that everything stays consistent with the rest of this tutorial and make sure all the dependencies are compatible, I would recommend using the dependency versions that we have here in our cargo toml. So now we'll also add in the Solana program. So we'll do cargo add Solana program. And if you want to specify a specific version, we'll just do that at for the version that we want. So we're going to use 1.18.17. Okay, and now our Solana program is updated. And now another thing that we're going to need in our dependencies is the init if needed feature for anchor link. So I'll explain what this does later on when we're actually using it, but for now, let's just get our cargo set up. We're going to do cargo add anchor link and add the feature flag. And this will just be init if needed. Okay, and you can see that the dependency was updated with the feature init if needed. And one last thing to update in our cargo toml is our IDL build feature. So because we're using the Anchor SPL crate, we also need to update our IDL build to work with Anchor SPL. So in our IDL build, we'll just add Anchor SPL -IDL build. Now our cargo is up to date and we can navigate back to our librs. So let's think about what we're building here. We're doing a vesting contract, and as we explained in the introduction, is we have two perspectives. We have our employee perspective and our employer perspective. So first, we're going to think about the employer. We're going to be creating a vesting contract, so we have to initialize that, and then we also have to add in the ability for the employer to add employees. And then lastly, we need to allow for the employees to be able to claim their tokens once they have vested. So let's start with initializing a vesting contract. So we can first define the instruction within our program macro, and we'll just do pub-fn, and we'll name it create vesting account. Whenever you're defining an instruction, you always have the first parameter is going to be your context. So we're going to just define the context, and then we're also going to want to create a custom data structure for this context. So we'll name that data structure create vesting account. And it will return a result. And then we'll write the logic for our instruction, but first we need to define what this data structure is. So outside of our program macro, we can go down here and we'll use derive accounts, and we're going to just define the struct. So pub struct, and this will be create vesting account. And we need to make sure we use the lifetime specifier. So what this context is doing is it is passing through all of the accounts that are needed to process the instruction that you're writing. So let's explain all the accounts that we need. First, we need the signer. So we'll write an account, and we need that to be mutable because the signer is going to be paying rent. So their account state is going to be changing when their balance of SOL changes. So we'll name them signer, and then the type is going to be a signer with the lifetime specifier. Okay. So one thing to note when we're writing all of our accounts is that with Anchor, each account used in a transaction, it's declared in a context structure with specific traits, and these traits dictate how the account can be accessed, like mutability, which is why we needed to specify the mutability for the signer because their account state is going to be changing, and in Rust, as you know, all variables are immutable by default. So here, when we define our account macro, we're going to have to specify all the constraints for the next account that we're writing. And we're going to be defining our vesting account, which is what we're creating with the instruction. So because we're creating the vesting account, we want to use the init constraint to specify that we're initializing an account when we're writing the instruction. So let's use our account macro. And then inside, we're going to first specify init. Now, whenever you're initializing an account, it's going to be taking up space on chain, and that space you need to pay for in rent. So we need to be able to calculate the space. So we can just define the space constraint, and we'll do the anchor discriminator, which is 8, And then we have to be able to calculate how much space that it's going to take up. And that's going to be defined by what you're actually putting into this account struct. So one thing that we do need to specify is what is this vesting account going to be. This is a custom-made account, so we're going to pause from writing this data structure and we'll just go down to define what our vesting account is actually going to be. So on Solana, all smart contracts are stateless. Every state is stored within accounts. So here we're creating a vesting account that is going to store all of the information for a specific vesting smart contract. So what do we want to store? We're going to first define that it's an account. We're going to use the account macro from Anchor. We're going to name this vesting account. Okay. So this is a vesting account for an employer for all of their employees at a company. So what do we want to save here? First, we want to know who the owner is. So that's going to be whoever has special permissions to update the vesting account. So we'll save the owner, and that'll just be the public key of the owner. And now we're going to be distributing SBL tokens. So we want to save what the mint is for the SBL token. So that will also be a public key. And now this is just an account that's storing state. We're also going to need an account that's storing the SPL tokens. It'll be a token account. So we want to be able to store what the public key of that token account is within our vesting account state. So let's just do public key, we'll just do pub treasury token account. This is just going to be the treasury account of an employer's tokens that are all going to be allocated to employees that are working and receiving vested tokens. So this will be the treasury token account. The type will be public key. Okay. Another thing that we'll want to store, just for referencing, maybe creating a PDA in the future, is the company name. So we'll write company name. And that'll just be a string that can be a user input value when they're creating their new vesting account. And then we also want to save the bump, and we'll save the bump for both the treasury token account as well as the vesting account. So we'll do bump for treasury. And that's always a U8 type. And then just the bump for the vesting account, which is also a U8 type. So now we have the account, but how are we going to actually calculate the space? Anchor actually has a way to do that. So this account macro is an attribute applied to the data structure to designate that it's a Solana account. And then we can also add the derive macro, and it's an implementation onto this account data structure. And we can specify that we want to use a init space. So we'll just do derive and then a init space. And what this does is Anchor automatically calculates the space for you. Now you can see that when I wrote that, we have an error that was generated. And that's because the company name is a string value, and a string can be extremely long. So we're going to want to designate a max length for what this string can be. So I can just go in here and actually write max length. And I'm just going to say 50. Seems good for a name. Now that error went away, and now we have our account fully defined. So now that we have that, when we're calculating the space in our create vesting account struct, we can just use the init space. So that's going to look like just the name of the struct and then a init space. Okay, so now that we have the space calculated, we need someone that's going to pay the rent. So we just have to define who the payer is. And that's going to be the signer of the instruction. And now we're creating a new account. So since we want to be able to derive the PDA in the future, we need some type of attribute that differentiates the different PDAs for a specific signer. So here we're just going to use the company name. So we can do seeds, and we'll use the company name as ref. And then lastly, because we have the seeds, we need the bump. And then we're going to just need to define what this account is. So we'll name it vesting account. And it will be an account with the lifetime specifier, and it's going to be using the vesting account struct that we defined right here. Now, there is an error, and the reason for that is because we're passing through a company name, and this struct doesn't know what it is. So yes, we need to update the input parameters from the instruction first, and just say we're allowing on the front end someone to type in what the company name is. That'll be of type string. But this still isn't passed through down here. So to be able to pass this information through our context data structure, we're just going to add this macro that is basically saying we're pulling this variable from the instruction. So we'll do the instruction and then name the variable. So we're using the company name of type string. Okay. The next thing we're going to pass through is just the mint account, and that's going to be what the SPL token mint is for the vested token for this specific vesting account. And we're going to be using interface accounts here. And it will be a mint type. So we need to import this mint, and this is coming from our SPL token crate. So you can see here, anchor SPL token, mint. But actually, we're going to be using the token interface rather than the token. So we'll go down to anchor SPL token interface mint and import that. So you can see the import updated. And you can see the vesting account still has an error, and we'll get to that in a second. But basically, whenever you initialize a new account on chain, you do need to pass through the system program. But we'll pass that through towards the end. So far in our context data structure, we're passing through the signer who is signing the instruction. We're passing through the vesting account that we're creating to hold all of the state for the new vesting account. We're passing through the mint of the SPL token that we're vesting. Now, we also need the Treasury token account that's going to store all of the tokens that are going to be handed out to employees. So we can initialize that at the time of running this instruction. So we're once again going to use the init constraint on the account. And now here, it's going to be a little bit different because it's a token account. So we're going to need all of the information for the token. We can do that by running the token constraint. And we'll define what the mint is for the token. And that mint is going to be the mint that we just passed through above on the previous account. Okay? And now we also need the authority for the token. And that authority is going to be the token account itself. So in the future, when we're actually transferring the tokens, the token account has the ability to transfer to the employees. So we'll set the authority to the Treasury token account, which is what we're going to name this account. Okay. And now we just need the payer, which will be the signer once again. And then here we're going to define the seeds. This is going to be a token account, not an associated token account. This is because it's going to be a token account specified just for this vesting contract. So we want to create seeds for the PDA that will make it easy to derive. So we'll make the seeds state that it's the vesting treasury, and we can do that by just typing out vesting treasury. And then we'll also want to add in the company name as ref. Okay, a little typo, let's fix that. There we go. And now because you specified the seeds, we also have to add the bump. And now all the constraints are defined, so we just want to state what this account is, and that will be our Treasury token account. And now we're going to update this to an interface account. And then the type will be a token account. So now we have our Treasury token account, our vesting account, we have the signer, we have the mint. So all that's left is two things, our system program and then the token program because we're creating a token account. And this token program is actually going to be an interface, and we're going to use token interface. And now you can see we have one more error left, and that is we need to import token account. So we'll just import that. And that's going to come once again from the token interface. Okay. And because we're using a string here with vesting treasury, we're going to update this. Instead of as ref, it's going to be as bytes. And that's everything for all of the accounts that we need for the first instruction to create a new vesting account. So now we can write the logic out for creating a vesting account. And you can see here, there's a warning generated for a company name, and that's just because we haven't used it yet in the logic, and Rust always wants to warn you if you're passing through a parameter and it's not being used. So the first thing we're going to do is just load in the vesting account, and we want to be able to update the state. So because the context holds all of the accounts for this instruction, all we can do is just load in the context dot accounts, and we can point to the vesting account. Now what we need to do is we need to dereference this. So we can add this asterisk, and that is a dereference operator in Rust. And what that does is it dereferences the account that it's pointing to, which is the vesting account in our case. And it allows you to modify the account. You need to do this because it's an account reference. You need to dereference it to be able to modify it. And this tells Rust that you want to work with the actual data and not just the reference. So now you can update values of the actual data of the vesting account. Now we'll just pull in the vesting account type. Okay, and then we can just update all of the fields within vesting account to save the information for the new account that we're creating. So first we'll do owner. And that will just be the key of the signer. So we can pull in the signing account and then just grab the key. Now we need the mint. And we'll just pull in the mint account and grab the key. Now we need the treasury token account. Once again, we'll pull in the treasury token account, grab the key. And then the company name is just going to be the company name that's passed through. And then we'll just grab the bump of both the treasury and the vesting account. Okay, sometimes Copilot tries to autofill things and it's not always correct. So we're going to fix what Copilot just wrote. And we're actually going to pull this in by doing ctx.bumps. And we're going to pull the bump of the treasury token account. Okay, and then we need the bump for the vesting account. So ctx.bumps.vesting account. Okay, and I spelled account wrong, so we'll just fix that typo. There we go. And then we're just returning an OK for our result. And that's everything we need for our first instruction. So you can see that most of the logic here happened within our create vesting account data structure because that's where all the accounts are handled. So if we go back down to our create vesting account, you can see we've set up both our vesting accounts and a token account for the treasury. And then the logic within the instruction is just saving all the information that we need to the account state of the vesting account. So first instruction is done. Now we can move on to the next. So not only do employers need to have a vesting account, but employees need to have a vesting account as well. And that's going to hold different information. It's going to hold all the information for their vested tokens, like the cliff time, how many tokens they have allocated to their public key, and anything associated with their token vesting. So that's going to be input by the employer of what their specific allocation is, and then the employee needs to be able to access that to be able to claim their tokens. So let's create the employee vesting account. Now, because we're creating a new account, let's define what is being saved to the state. We're going to do the same thing that we did with our vesting account by defining what the account is. So we'll use the account attribute that just tells that this is a Solana account. Okay. And then we're once again going to use derive init space because we need to calculate how much space it's going to take up on chain. Okay. And then we'll just define what this struct is. So this will be the employee account. So what do we want to save here? We want to know who's going to be able to claim this. So let's define what the beneficiary is. And that'll just be the public key of the employee for this specific account. So typically when you create a vesting account, you want to keep track of when the allocation started, when it's going to end, and what the cliff time is. So let's define all of that first. So the start time. Now this is all going to be stored in Unix time, which is an I64 type. The end time, also an I64, and then the cliff time. And what the cliff time is just how much an employee has to wait before any of their tokens unlock. And then once the cliff passes, it typically unlocks linearly after. Now, we'll also want to keep track of the vesting account. And this is just the corresponding vesting account that was just created by their employer. So that will be a public key because it will be the account address. And now we just need to know how many tokens are being allocated to the employee. So we'll do total amount. And that will be a U64 type. And then we want to keep track of how many the employee has withdrawn from their account. So we're able to calculate at a specific time how much they're able to either claim or how much they still have left to claim in the future. So total withdrawn. And that'll be a U64 type as well. Okay, so that's everything we're going to be storing to the state for the employee account. Now we can write the instruction to create this. So pub fn, and now we're going to create employee account. Okay, so we'll pass through the context as our first parameter, as always, when writing an anchor instruction. Define as a context type, and then we're going to create a data structure for create employee account. So let's pause from this instruction and go down here to write our derive accounts data structure. So pub struct create employee account. Add in our lifetime specifier. So now we want to know who the owner of this employee account is going to be. So the owner is actually going to be not the employee, but the employer, because the employer is going to be the person who has access to update the allocation information for a specific employee. So that's why we're going to update. The signer is going to be the owner. And once again, it needs to be mutable because we're creating an account, so the signer has to pay rent for that account. So we're going to set the signer as the owner. Okay. Now we also need to know who the beneficiary is, which is the employee that's going to be able to claim tokens later on. So let's pass through the beneficiary account. And that'll be a system account. And we'll add in the lifetime specifier. Okay. Now we need to pass through the vesting account. And that is because we're going to need all of the information from the vesting account state. But one thing we want to do is we want to use the has one constraint to just make sure that the owner of the vesting account is the signer of this instruction. And that's just validating that the person with the correct access is going to be able to run this instruction. So we'll do the account attribute and add in the has one constraint. And set that to owner. Okay. So now we have to actually create the employee account. So we're going to use, once again, the init constraint on the account. So account init. And this is just an account that is holding state, so we don't need to use the token constraint. And we're going to specify what the space is. We'll use the 8 discriminator from Anchor. And then we can just use a init space to calculate the rest. So employee account, init space. And then because we're taking up space, we need to pay rent. So we need to define who the payer is. And then we're going to define the seats for our PDA. So here, let's use employee vesting. And then we're going to add in the beneficiary key as ref. And then the vesting account key as ref. And now that we have C's, we also need a bump. And then all that's left is just to name what this account is. So it'll be our employee account. Okay, and now we have an error here, and that is because we need to define the system program whenever we're initializing a new account on chain. So we'll pass that through, and now our error went away. And that's everything we need for an employee account. So we can go back to the instruction and finish the logic there. Okay, so we'll load in the account the same way. We need to dereference, call the context accounts, and employee account this time. We'll use the employee account struct. Okay, and now we need the beneficiary is the first field. And that'll just be the context accounts beneficiary key. And we have a typo, it's accounts with an S, there you go. And now we need the start time and the end time, but we don't know what that is. So we want to update our parameters to include start time and end time. And this will be passed on the front end. Okay, so we have our start time, we have our end time. Now we also need to pass through the total amount. So let's add that. That's a U64 type. Okay, and then the total withdrawn, since we're initializing a new account here, it's impossible to have withdrawn anything, so we'll just set that to 0. And then we need the cliff time, we'll pass through as a parameter. And now we need the vesting account, and we'll just pull in the account's vesting account key. And lastly, let's save the bump. Now this will be the bump of the employee account, so we can just do ctx.bumps employee account. Okay. And now we just need to return OK. So now we have an error, and it's saying there's no such field as bump, which means we forgot to define the bump in our employee account state. So we'll just go here and add that field because we always want to save the bump. There we go. So everything's good for creating an employee vesting account. Now, the last instruction that we need here is allowing the employee to come and claim tokens. So this will have a little bit more logic to make sure that an employee can claim tokens at the correct time. So let's start by defining this instruction. We'll do pub fn claim tokens. Okay, so we'll pass through the context as the first parameter, and then we'll go down and define what that is. So claim tokens. And now we can do derive accounts for claim tokens. So this will pass through all of the accounts that are needed for an employee to be able to come to this program and claim tokens. So first we need the signer of the instruction. And in this case, instead of it being the owner of the vesting account, we want it to be the beneficiary of the employee account. So we'll update this to account. It needs to be mutable. And it will be the beneficiary, and that will be the signer of the instruction. And next we need the employee account. So we can define the account. And here we're going to need to update information in the account state because we'll be updating total withdrawn if an employee withdraws tokens. So we want to make the account mutable. And now we need the seeds. So this will be the same seeds from the employee account. So just to make things easier and make sure we have all of the correct information, we'll go back to when we initialize the employee account and just copy those seeds over. Okay, so this is employee vesting, the beneficiary, and the vesting account. And now we need the bump, and because we saved the bump when we were initializing, we're able to just pull that information. So we can do employee account dot bump. Now we're going to need to do 2 checks on this account. We want to make sure that it has the correct beneficiary, so only the employee that is the beneficiary of this employee account is able to come in and run the instruction and claim tokens. And then we also want to make sure that this is connected to the correct vesting account that's being passed through. So we'll do has one beneficiary, and we'll also do has one for vesting account. Okay, so we'll just define this as the employee account. Now there's a few things here that we haven't defined yet. So the beneficiary was already passed through as the signer, but we need to define the vesting account. And the vesting account is used twice, so we want to just make sure that that account is passed through so it's able to pull the correct information. So let's pass through vesting account next. And we need the seeds for the vesting account. And we'll just do the same thing. We'll go back to when we initialize the vesting account and copy over the seeds. And then because we saved the bump to the vesting account state, we can just grab that information. And then we're going to do 2 checks here as well. So we want to make sure that this vesting account has the correct token account that's being passed through, and that is the Treasury token account. So when this claim happens, it's going to be transferring SPL tokens from the Treasury account into the employee token account. So we need to pass through the correct Treasury account to be able to pull those tokens from. So we'll do has one and the Treasury token account. And then we also want to make sure it has the correct mint address of the SPL tokens. So we'll do has one mint. So then we'll just define this account, and that's the vesting account. Now, there's a few things that we haven't defined yet. So one is the company name. Now we're going to have to pass through the company name as a parameter from the instruction. So let's go back up to the instruction and let's add in company name here. And then for this data structure to be able to recognize that information, we have to pass through our instruction with the company name. Okay, so now you can see that error went away. Now we need both the Treasury token account and the mint account to be passed through. So let's do the mint next. And that will be an interface account, mint. Now we need the Treasury token account. So this also has to be mutable because we're going to be changing the token account balance. And all we have to do is just define what this is. So Treasury token account, it's an interface account, token account. Okay. And now you can see both of those errors went away and all the accounts are passed through. Now, what else do we need? So we have the beneficiary, we have the employee account, we have the vesting accounts, we have the mint, and we have the Treasury token account. So it seems like there's one important thing that's missing, and that is the employee token account. So we have the account state for the employee, but we don't have where the tokens are going to be sent to. So what we can do is create an associated token account. And this is where the init if needed constraint is going to come into play. So let's first define the account. And instead of init, we're going to use init if needed. And that's because some users may already have their token account for the specified SPL token created. And if they do, it's going to just bypass the init constraint and continue with the rest of the logic for the instruction. But if they don't already have this initialized, this account will then become initialized after running the instruction. Now we'll need the payer because it has a init if needed. So if the user doesn't already have this account initialized, then we need a payer to be able to pay rent for the account. Okay, so in this case, the payer is going to be the beneficiary because it's their associated token account. Now we're going to just define what the associated token account is. So we'll use the associated token constraints. And first we want the mint, and that'll just be the mint address of the mint account that we're passing through. And then we also want the authority. And that'll be the beneficiary because it's their own token account. And then we also need to define the token program. So associated token, token program, and that will just be the token program. And now all that's left is to define what this account is, and this will be our employee token account. And because we're using the token interface, this will be an interface account, token account. Okay. Now, one thing is missing is what is the token program? So let's define that. And the token program is an interface, token interface. And now because we're using the associated token constraint, we also want to pass through the associated token program. And this is associated token. And then lastly, because we're potentially initializing a new account, we want to pass through the system program. Okay. And now that error went away. And this should be all of the accounts that are needed for claiming a token. But let's just double check. So we have our beneficiary, which is the signer. And we want to make sure that the beneficiary is the signer because we only want the beneficiary of the specified employee vesting to be able to claim tokens. And then we have the employee account, and that is just all of the state of this employee's vested token information. We're doing a check to make sure the correct beneficiary is signing, and also it's connected to the correct vesting account to grab the information for the mint and the company. Now we have the vesting account being passed through. We're checking the Treasury token account is passed through correctly, and that's needed to be able to pull tokens from to send to the employee. And then we have the mint, which is to know what SPL token we're sending. Now we're passing through the mint account. We're passing through the Treasury token account. And then we're creating, if needed, an employee token account, and that's the token account that's going to claim the SPL token for the vested token. And then just the token program, associated token program, and system program need to be passed through. Okay, so that looks like everything. Now we can go back to the logic needed to claim tokens. We can return the result. And I like to always, before writing all of the logic, just have our OK return value at the end so Rust doesn't get angry with us and have a bunch of errors as we're writing. First, we need to load in the employee account to get all of the information for the vested token. So let's load in the employee account. And here we're going to do a mutable reference. That is because we need to specify that the referenced account is going to change information. And let's do ctx accounts.employee account. Okay, so that loads in our employee account. It's being stated that it's a mutable reference. Now, earlier when we loaded accounts in, we used the dereference operator, but here we're using a mutable reference. So let's talk about the difference between the two as we're writing this out. So dereferencing is used when you need to manipulate the actual data stored in the reference location, and it's kind of less common at a high level operations, and it's mainly used when you're initializing or resetting account data. Earlier, we were initializing two accounts, so we were using the dereference operator. But here we're borrowing a mutable reference, and this allows you to pass employee accounts around in your function or to other functions while still having the ability to modify the original data. And this is useful when you're using multiple operations on the data, which we're going to be doing as we're calculating to be able to claim tokens. When you're claiming tokens, the first thing you want to know is the current point in time, so we can know if an employee is able to claim tokens or not. So let's first use the clock to figure out what the time is. So we'll do now is equal to clock.get, and we'll unwrap, and we need the Unix timestamp. Now I want to check if the current time is before the cliff time, because if it is before the cliff time, then no tokens can be claimed. So if now is less than the employee account dot cliff time, we want to return an error. And now we're going to create a custom error for this program. And we'll name it claim not available yet. And it's always important to define custom errors when you can, because it allows a user to understand more of why they're getting an error when they're interacting with the smart contract. So we can define custom errors by using the error code macro from Anchor. So we'll just do error code. So this error code attribute, it's applied to the enum that it's attached to generate a result type T or an error type. So that's used to return errors for the program. Okay, and we're using an enum here because you're only going to be calling one error at a time. Okay, so we'll do claim, We'll copy in the error that we specified just to make sure everything matches. Okay, and we can add a message that's going to be displayed for the user. So we'll do message, claim not available yet. There we go. And now you have a custom error in your program. Okay, so next we're going to have to start doing some calculations, but when you're running calculations in Rust, we have to add some additional checks. So we need to take into consideration both underflow and overflow errors. Underflow occurs when calculations result in a number that's smaller than the minimum value that can be stored in the data type. And overflow occurs in the reverse, when a calculation results in a number that's larger than the maximum value that can be stored in the data type. So we're going to use specific methods when we're writing out these calculations. So let's first calculate the amount of tokens that are able to be claimed. First, we're going to define the time since the start of the tokens being vested. So we'll do time since start. And we'll do now. And instead of just subtracting, we're going to do a saturated sub. And what that does, it just ensures that the subtraction doesn't go below 0, which can help prevent underflow errors. So we'll do dot saturating sub, and we'll be subtracting the employee account start time. And this is an I-64 type because it's in Unix time. And now we need to find the total vesting time. So we'll do let total vesting time. And this will be the end time minus the start time, which gives you the total time period that the tokens are vested for the employee. So employee accounts dot end time. And we're going to subtract using saturating sub, and that will be subtracting the employee account start time. Okay. Now we're just going to do a little bit of error handling first. So we want to check to see that there is a total vesting time. So we're going to do, if the total vesting time returns 0, then the vesting period was invalid for the employee. So let's just do that check first. So if total vesting time is 0, and this is also going to help with calculations in the future because we don't want to divide by 0 anywhere. So if total vesting time is 0, it will return an error. And we'll once again write a custom error code. So we'll do error code invalid vesting period, we'll call it. And now we'll just add that to our custom error enum. So we'll go down to the error codes enum and add invalid vesting period. And we'll add the message. Okay. And we'll go back to our instruction logic. Okay, so now we want to know the total vested amount of tokens, which is the total amount of tokens that the employee can claim. So we'll do let vested amount equal. Now, if the current time is after the end time, then all of the tokens have unlocked. So let's do a check for that. So if now is greater than or equal to the end time, then we're going to just return the total amount. And then else, we're going to do a match statement. And that's because we want to make sure that all of the calculations are safe and we're handling possible errors. So we're going to type it out like this. We'll do match, and then we'll take the total amount and multiply it by the time since start. So employee dot total amount. Employee account dot total amount and we're going to use checked multiply. So checked multiply is a multiplication, and the checked prefix allows you to handle possible overflow errors. So checked multiply and we're multiplying by the time since start. Because the time since start is an I-64 type because it's in Unix time, and the total amount is a U64 type, we're going to cast the I-64 as a U64. And you can do that by just typing as U64. Because whenever you perform any calculation against variables in Rust, they have to be of the same type. Now, we'll do sum if the product of this multiplication we're just going to divide the product by the total vesting time. So what we're doing is we're taking the total amount, multiplying it by the time since start, and then dividing that by the total vesting time. Okay. And then if there's a none value. So the reason we're able to do this is because checked multiply, if there is an overflow error, instead of panicking, it returns a none value. So here we're just doing a check in our match statement. If it returns a value, we're going to be able to divide. If it returns a none, we're going to have to handle that error. We'll just return an error. And we'll make another custom error. And we'll name this one calculation overflow. And then we'll go back down to our error enum and add in the calculation overflow error and add a message. Okay. Okay, 1 second. My VS Code is being a little slow to update, so we'll just let that update. Okay, so just to recap this calculation, if we didn't perform a match statement here to check the product of your multiplication, then this checked mul is just going to return a none value, and then we wouldn't be able to do the division by the total vesting time. So by implementing the match statement, you're able to check to see if there's a product returned, and if there is, then you do the division. If there isn't, then you're handling the error of a none value being returned. Okay, so that looks good to me. Now we want to find what the claimable amount is for the user. So we found the vested amount. So this is how many tokens at the current point in time are unlocked. But if a user came in earlier and already claimed some, we want to be able to handle that. So what we're going to do is find the claimable amount by taking the vested amount and subtracting the total withdrawn value that's stored in the employee account state. So we can do let claimable amount So we'll do the vested amount, and then once again use saturating sub. And we'll do the employee account total withdrawn. Okay. And now a little more error handling. If the claimable amount is 0, we want to be able to let the user know that they have nothing to claim at the current point in time. So we'll do we'll do if claimable amount equals 0, then we're going to return an error of, and we'll do the error code, and we'll make a custom error called nothing to claim. And then we'll update our error code enum down here with our new custom error. So VS Code is being a little slow to update. All right, there we go. Now the error went away. Now we did all the calculations needed, so we now know what the claimable amount is for the user. And now that we know what that is, we can actually process the claim. So by doing that, all we're going to be doing is a transfer of SBL tokens from the Treasury account into the employee's token account. So we can do that by making a CPI call. A CPI call, it's a cross-program invocation, and it allows you to make calls from another program. In our case, the transfer is from the system program. So we can do let transfer CPI accounts And we're going to define all the accounts needed for this transfer to take place. Here we're going to use transfer checked. And we want to make sure this has the correct import, which VS Code is once again still being slow. So instead of using the quick import, we're going to manually import. Looks like there was a weird import generated. Okay. So all we're going to do is update our token interface from the Anchor SPL crate to include transfer checked. Okay. Now we can go down here. And you can see from the structure, we need from, mint, to, and authority. So we'll define all of those fields. From, so the tokens are going to be coming from the Treasury token account. So we'll load in the context account, Treasury token account to account info. Now the mint is the next parameter. And we'll just do the mint account. And then we have to, and we have the authority. And in this case, the authority is going to be the Treasury token account. And that is because when we earlier initialized the Treasury token account, when we used the token constraint on the account attribute, we specified that the authority was itself. So here we can just set the authority to itself. Okay. So those are all the accounts that are needed for the transfer. Now we can define the CPI program. So let CPI program equal, and that is going to be the token program. So the transfer instruction that we're calling from the cross-program invocation is coming from the token program. The next thing we're going to have to do is define the CPI context. But first, to be able to sign the CPI context, we need to define what the signer is. In our case, we had a PDA for the Treasury token account. So we need to now derive that PDA to create our signer seeds. So let's do signer seeds. And the signer seeds have an interesting type, so we're going to explicitly define that type here. And all it is a few references. So 1, 2, 3, and a U8 type. Okay. So now we can go back to what our seeds were, which is for the Treasury token account. When we created it, let's go to that context. Right here. So I'm just going to screenshot this so we can reference it and make sure we have the correct seeds. So we've first had our vesting Treasury. Vesting Treasury. And then the next field was the company name. So we can load that in from our context. So we can do context.accounts dot, and the company name was saved in our vesting account state. So we're going to use the vesting account. And then within the vesting account was the company name. And then lastly, we just need the bump defined. So we're going to reference the context.accounts. This is for the Treasury account, and we saved the Treasury bump into the vesting account state. So we're going to call in the vesting account. And then from that, we're going to pull in the Treasury bump that we saved to the state. Okay, so one thing we were missing was adding a reference to the seeds. So we'll add that in. And now we'll just double check. We have our initial reference. We have the second reference for the seed. And then we have the last reference for the bump. Okay, and actually the bump lives inside of this. Okay, there we go. So now we have 3 nested references, and that is our signer seeds for the Treasury token account. Now that we have that, we can define our CPI context. And this will be a CPI context new. And the first parameter is going to be the CPI program. And then we need the accounts. And now we need to specify that it's with signer because it is a PDA, so we need the signer of the PDA. So with signer, and this will be the signer seeds that we just derived. Now, lastly, we need the decimals of the SPL token that we're transferring. And that we can just take from the mint account that's passed through. So we can do context.accounts.mint. And then decimals. Okay. Now we can actually process this CPI. So we're going to use the token interface. And we'll do transfer checked. And we'll pass through the CPI context, the claimable amounts, and the decimals. And now let's make sure the claimable amounts is of a U64 type. So we'll just do, we'll cast as a U64. Okay, it looks like the signer seeds type may be off. So we're just gonna update the spacing here so it's easier to read. So we have our signing seeds, and we have our reference. Oh, okay, we're just missing a comma here. There we go. Okay. Now we need to import the token interface. So the token interface is coming from the SPL token interface. We'll update the interface here. So this should just have self. Okay. Now we performed our CPI of transferring tokens from the Treasury token account into the employee token account. And all we have left is just to update the account state for the employee to reflect that we've withdrawn tokens. So we'll add employee account dot total withdrawn and increment that by the claimable amount. And there we go. So that is everything for our instructions. Now, one thing to notice is in our parameters, we have company name and it's returning a warning. And that warning is because the company name is not being used within the instruction logic. But we need to tell Rust that we know it's not being used, but we're using it somewhere else. So to do that, we're just going to add an underscore here. So just to recap, we've created vesting accounts for the employer. We've created employee accounts for the employee to be able to claim their allocated tokens. And we've created an instruction for employees to be able to come to the UI and grab the tokens that are claimable. So now let's do an anchor build to make sure that the program builds. So we need to remember to be in our anchor folder to do any instructions that are related to anchor. Okay, so we can run anchor build. Okay, so we can see that the code compiled everything's good to go. There was a warning generated. So this is just trying to help with formatting. So we can go and make that update with the warning. If we go to our match statement, there were some parentheses here that just aren't needed. So we can get rid of those. Clean that up a bit. There we go. Okay, so we can just one more time run anchor build. It'll be a lot faster now that it's already compiled once. So now that we've built our new program and everything compiled correctly, we can start testing. But first, let's go over everything that happens within this anchor folder. So when you run anchor build, it updates the target folder. So you can see here, the target folder is now green, meaning there are new files generated. And we can go into our IDL, and now there's an IDL created for the vesting contract that we just wrote. We have this counter IDL from the previous counter program that was generated with the scaffold, and we can just delete that because we don't need it anymore. And we'll just keep the vesting IDL. Now, there was also a types file generated. We can once again delete the counter file. And what this vesting types, it's a TypeScript file that's compatible with your TypeScript that uses the program IDL. These two are going to be using for both our testing and our front-end application because both of those are going to be written in TypeScript. Now, all of that's done. So let's start with our tests. There is a counter test that's already generated. We're just going to delete that because we no longer have the counter program and we're not writing normal TypeScript tests. We're going to be using Bankrun here. So let's get everything set up for our Bankrun tests. So what this does is it creates a Banks client and a Banks server and runs our tests against it. Now, we're going to have to specify the path of our program to be able to deploy the program to the Banks client and run the test correctly. So let's make a fixtures folder inside our test folder. And what that'll do is we'll just import our vesting.so file. So if we go back to target and we go to deploy, you can see our .so is generated. So we're just going to copy that and paste it into the fixtures folder. And this just allows the Bankrun test to be able to easily access our .so file of the smart contract that we just wrote. And just to clean up a little, you can see the counter key pair, anything counter related. If you see it, just delete it. Okay. Now inside our test folder, we can create a new file, and that's going to be our Bankrun test. So we'll do bankrun.spec.ts. Okay. Now there's a few packages that we're going to want to install to be able to use Bankrun. So in our anchor folder, we're going to npm install. And we want, let's see, what do we already have? We'll go to our package.json. And we have Anchor, we have Web3.js. So now we also want to add in the SPL token. So we'll do @solana.spl token. Okay, so you can see there's some dependency issues. So what we're going to want to do is define a specific version. So we're going to do @Solana SPL token, and we'll do .4.8, and we're going to update our Web3.js to 1.94.0. Okay, great. Now we're going to install Anchor Bankrun. Okay. And that'll be version 4.0. And now we're going to install Solana Bankrun as well. Okay. And that'll be version 2.0. We're going to update the version here. So this is just making sure we have compatible versions for all our dependencies. And then because we're going to be using the SPL token when we're testing, we want to also use the SPL token from Bankrun. So we'll npm I SPL token Bankrun. Okay, and this one, we're also going to update the version to 2.5 instead of 2.6. So let's see, we have our Coral anchor, we have Solana SPL token, version 4.8, we have Web3.js version 1.94, we have Anchor Bankrun, Solana Bankrun, and SPL token Bankrun. Okay, so those are all the dependencies we need for our Bankrun tests. And let's just make sure everything's properly installed. Okay, great. Now we can go back to our Bankrun file and start writing our tests. So first thing, we're going to just set up our test. So we'll do describe, and then we'll name the test vesting smart contract test. Okay. Before we start actually running the test, we first want to start with our environment setup. So in our environment, we want to make sure we have an SPL token mint that we're going to be using with the proper authorities. We also want to make sure we have the right programs deployed to be able to test our vesting contract properly. So let's set up our environment first. So we're going to do that by using before all. And what this is going to do is run these specific functions before every single test is being ran. So this is going to be an async function. Okay. Now within the Bankrun test setup, you have a wallet with a payer that is already funded and ready to be able to work. But in our smart contract, we have two different scenarios that are being tested. We have the employer perspective as well as the employee perspective. So we'll keep the default native wallet within the test to be for the employer. But now we have to set something up for the employee. So let's name this beneficiary. And we're just going to generate a new key pair. So we'll do new anchor dot web3 dot key pair. Okay. So we need to first define the type. So outside of our before all, we're just going to let beneficiary be of a type pub key. Okay. And this is TypeScript, so the type is actually public key, not pub key. We're not in Rust anymore. Public key. Okay. Now let's fix our imports. So we're going to make sure we import public key from Web3.js. We also want to import Anchor. So we'll define our first import here as Anchor, and we're going to fix Copilot suggestion, and this should be from Coral XYZ Anchor. Okay, and now we have a typo in key pair, so let's fix that. There we go. And this is actually a key pair, not a public key. So there you go. Now, one thing to note, the difference between a key pair and a public key. The key pair has both a private and public key attached, so you're able to sign with it. And because we need the beneficiary to be able to assign instructions, it needs to be of a type key pair to be able to sign those instructions. Okay, and we're just updating our imports. We'll just keep the public key import there because we will be using that in the future. So we've defined the beneficiary. So next we're going to define our context for Bankrun. So we can do that by await start anchor. Now we'll define what the context is. And the context is your program test context. So program test context. And we'll import that. So the quick import isn't showing up, so we'll manually write that. This is going to be an import from Bankrun. So we'll do import program test context from, and this is going to come from Solana Bankrun. Okay, so we'll be defining our context. We're going to do that with start anchor, and what start anchor does is it starts a Bankrun in an anchor workspace with all of the Workspace programs deployed, and it spins up a bank server and a bank's client, deploys the programs and all the accounts that are added. So let's import start anchor, and that's going to come from Solana Bankrun. And let's update our program test context to import correctly. Okay, there we go. Now we're going to update all of the parameters that need to be passed through for start anchor. So start anchor first has the path, which is the path to the root of the anchor project. And because we created this fixtures file with the vesting.so pasted into it, we're able to just make the path an empty string. And now the next parameter is going to be the extra programs. So the program that we need to deploy to Bankrun is going to be vesting. So we're going to set the name as vesting. And one thing to note when you're naming these programs, it needs to be whatever the name is of your .so file. So you have to make sure that those two values match or it's not going to pull the right program. Okay, so we have the name, and we also need the program ID. So program ID, and this is going to be of a public key type. Now, when we created our librs, you have this declare ID with a public key. This is your program ID. When you run anchor build, it creates an IDL, and within the IDL, you have an address. These two values should be the same. You can see that they are. And this is the program ID of the smart contract that we just wrote. So we can go back here and just pull that from the IDL. So we want to properly import the IDL. So we'll import IDL from, and it's going to be our target IDL vesting.json. That's the file path to get back to this file here. Now, in our program ID, we can just call that address. So we can do IDL dot address. Okay, and now we have a little typo. This should be on the other side. Okay, we passed through our parameters for the added programs. Now we need to pass through what our added accounts are. Now, we talked about earlier how we need to add a beneficiary account. With Bankrun, you already have a signing key pair that has both the public and private key with funded LAMP ports, and we're going to be using that for our employee. But now we have another perspective that needs to be able to sign instructions, and that's our beneficiary. So we generated the key pair for the beneficiary, but now we need to load that key pair in and make sure that it's funded with LAMP ports, so there are LAMP ports to be able to pay the gas fees when executing an instruction. So we can define that here. we'll first specify the address, and that will just be the public key of the beneficiary. And now we'll add in the info for this account. So this is just your typical info data structure. It's going to have the land ports, and we'll just fund it with a bunch of land ports. And then it's going to have the data, and then it'll have the owner, and in our case it's just going to be the system program. So we can actually import the system program ID from Anchor. And lastly, the executable, which we're going to set to false. And now we're getting an error here, and that's because we have a typo in ID, so it's just camel case program ID. Okay, so that's everything we need for our context. And just to recap, we have our start anchor that has the path to the root of the anchor program. We also have the programs, which is an array of the objects indicating which extra programs need to be deployed to the test environment. And we have accounts, which is just an array of accounts indicating the data that needs to be written to a certain address in this testing environment. So now we set up the context. Now we need the provider. So after context, we're going to define the provider. And this will be a new Bankrun provider. And the parameter is just the context that we defined in the previous step. Okay, now we need to make sure that first provider's type is defined. So provider is a Bankrun provider type. And then we just need to import Bankrun provider. And this is coming from Anchor Bankrun. So we'll do import Bankrun provider. From Anchor Bankrun. Okay, now that we have the provider, we need to set the provider. So we're going to do anchor dot set provider, and that will be the provider that we just defined. We have the provider, we set it. Now we need to define the program. So we have the program, and that's just a new program. And we want to make sure that it is matching the vesting IDL. So we'll add IDL as vesting, and we can import that vesting type from our TypeScript file that was generated. And the other parameter is the provider. Okay, so first let's define the program type. So program is program vesting. We want to import program from Anchor. Now we want to make sure we already did an import of the IDL, but we also want the TypeScript compatible version. So we're going to import vesting from the target types vesting. And this is our TypeScript file. There's two things that we're going to be using a lot throughout our test. So we're just going to simplify that by creating a variable for that. So one is the banks client. So one is the banks client, and the banks client comes from the context. So we can name banks client is the context.banks client. And now we'll define the type above. And that is a banks client type. Okay. And the next thing we need is the employer. So we talked about how the provider comes with a wallet that is already funded and has the full key pair of both the public and private key. So we can just name that employer, so we don't mix up our two signing keys that we have. So we have provider.wallet and then dot payer. Okay. And then we'll define what the employer is up here. And that will be a key pair because it is a signing key, just like the beneficiary is. Okay, so far we've set up our environment with the needed accounts and programs. But we also need to have an SPL token mint that we're going to use as the token that we're going to be passing back and forth between our Treasury accounts and employee accounts. So let's actually create a mint. And we need to create that so we have the mint authority to be able to mint tokens to the correct accounts. So we'll set mint. And we're going to await and we'll create mint. Okay. And this is an import from SPL token Bankrun. So we'll add that import. Import create mint. From, this will be SPL token Bankrun. There you go. Okay. So now the arguments that are passed through for create mint, we have the banks client, we have the payer, we have the mint authority, the freeze authority, decimals, key pair, and program ID. So let's define all of those. And first, before we do that, let's actually define the mint type. So we'll go back up here and do let mint, and the mint is going to be a public key. Okay. So now we have the banks client. Okay. And then up next is the payer, and in our case, that will be the employer that we defined earlier. And then we want the mint authority, so that is going to be the public key of the employer. For our testing purposes, we don't need to freeze any tokens, so we're just going to leave that as null for the freeze authority. And then for decimals, we'll just put 2. And I have a typo in banks client, so let's fix that. There we go. I have a typo everywhere in banks client, so we'll fix all of them. Okay. Now, there's an error, there's a type error with the banks client, and you can see here that it is between the Solana Bankrun and the SPL token Bankrun. So this is actually within the dependencies themselves. So what we're going to do is just do a TS ignore because it does work between the two. So we'll add in at TS ignore. Okay, now there's just a few more things to do to finish setting up our test environment, and then we can go to writing the actual instructions to test the smart contract. So first is setting up the provider for the beneficiary key pair, and we're going to be using a different program when we're actually executing the instruction for the instruction that the beneficiary needs to sign. So we'll just get that set up now. So we'll do beneficiary provider. So that is a new Bankrun provider. And we want to use the same context that we defined earlier, so we can just do context. Okay. And then we're going to do the wallet. So beneficiary provider dot wallet equals, and this will be a new node wallet of the beneficiary. Okay. Now we need to define what the beneficiary provider type is. So we'll go back up to the top. Let beneficiary provider, and that will be a Bankrun provider. And now we need to import node wallet. And this is coming from Anchor. Okay, and then we can just define this second program with the new beneficiary provider. So program 2 is equal to new program of type vesting. And then we'll need the IDL as vesting. And it's setting the provider as the beneficiary provider. Okay. And then we'll once again define the type for the new program. So let program 2 equal the program vesting type. And lastly, we just need to derive the PDAs. So we have 3 PDAs throughout our smart contract, and we'll just derive all of those now. So we'll do the vesting account key. And now you're able to find the address from the PDA by just using the find program address sync. And what this does is it generates the public key for a specific PDA. So public key dot, and we'll use find program address sync. And then we need to define our PDA. So for the vesting address, we used just the company name to create the PDA. So we can do buffer.from company name. And then we just need the program ID. So we'll do program.program ID. Now, 2 things. One is defining the type of the vesting account key. So we'll go back up to the top. Let vesting account key is a public key. And then the next thing is the company name. So since the company name is a user input value from the UI, we're just going to explicitly define the company name for testing purposes to make things easy. So we'll make a constant at the top. Company name is just, we'll make it company name for now. Okay, cool. So that's our vesting account key. Now we need a Treasury token account key. So Treasury token account. And we're going to do the same exact thing. So public key dot find program address sync. And this is where we define the seeds for a PDA. So we'll do buffer dot from. And for our Treasury token account, we did vesting Treasury as the first part of the seeds. So vesting Treasury. And then the second part was the company name. So buffer from company name. And then lastly, we just need our program ID. Okay, we forgot an equal sign, so we'll add that. And we need to define the Treasury token account type. So let Treasury token account be a public key type. Okay. And the last PDA we need to derive is the employee account. So let's define that. So same exact method. We have our employee account. And that is a public key dot find program address sync. And then the seeds for our employee account was a little bit longer than the rest. So we have buffer from, and it was employee vesting. Okay, and then we had the public key of the beneficiary. And then we had the vesting account key. So we had a typo in public key. So just for reference, the public key class has a capital K in TypeScript. Okay. And then lastly, we just need to define the program ID. let's just fix some formatting a bit. So this is a bit easier to read. Okay, there we go. And now we'll once again define the type. So this will be let employee account be a public key type. Okay, so that's everything for the PDAs that we need to derive. And it looks like we have everything set up for our testing environment and we can start actually testing. But let's just recap everything that we wrote. So before all, sets up the environment, and this is going to be ran before every single test that's ran. And here we're setting the beneficiary key pair. We're running start anchor, which is setting your Bankrun in the anchor workspace, and it's creating the bank's client and the bank server. It is specifying the path to your .so of the smart contract that we're testing. It's specifying the programs that we need to deploy, which in our case, it's just the vesting contracts. And then it's also specifying the accounts that need to be funded and have specific data written to it. And for our case, it's just funding the beneficiary account. We're setting our provider, running anchor set provider, naming our program, setting the bank's client. We're creating a mint address with the employer being the authority. We're updating the provider for the beneficiary. And then we're getting all of our program addresses for each PDA that we need to derive with the seeds that we're specifying. Okay, great. So now we can start writing our test. So we'll go outside of the before all and write our first test. So we're going to create a vesting account. Okay, and this is going to be an async function as well. And now we can write our first transaction. So we'll do const tx and await. And now we can just call the namespace from the program. So we'll do program.methods. And now we can call the create vesting account instruction. So create vesting account. And all we're passing through as a parameter here is the company name. So we'll write company name, which is a constant that we defined earlier. And now we need to define all of the accounts that need to be passed through to run this instruction. So when we're creating a vesting account, we need the signer, we need the mint, and we need the token program. So we're going to set accounts. And signer is going to be the employer, but it's going to be the public key. And then the mint is just the mint that we already defined. And then the token program and this is just the token program ID. There we go. So with the new version of Anchor, any account that is a PDA that needs to be derived, it automatically does that for you. So you're just passing through the additional accounts here. Okay, so now we need to send the transaction. So we'll do .rpc. And then the commitment is confirmed. Now we're just going to console log our transaction. So we'll do console.log and then creates vesting accounts, and it will be our transaction. So another thing we can log actually is the vesting account data, just to make sure that the vesting account was created correctly. So let's do const, we'll do vesting account data. Await program dot account dot vesting account, and we can fetch our vesting account key. Okay, and then we'll just console log that. Now we can run our first test, make sure it works. So in our anchor folder, all you need to do is run anchor tests, and it will run all of the Bankrun tests. So you can see it's recompiling the anchor program. And now it's running the test suite, and you can see our test passed. So let's go back to our logs. Within anchor Bankrun, so here's our test. It's running the Bankrun spec TypeScript file. It's running Solana program test. Here are your runtime messages. And then here's our console log. So the vesting account data, we have the owner is the public key. We have the mint address. We have the Treasury token account, the company name. We have the bump for the Treasury and the bump for the vesting account. And then we also have the transaction of our create vesting account. And you can see in our test suite, we have one test passed, and the test was named should create a vesting account. Okay, so now we can go on to the next test. So in our first test, we created the vesting account. Now the next instruction that we want to test is creating an employee account. So let's write that test out. We'll do it should create a... Actually, before we create the vesting account, we need to fund the token account. So let's think back at what we just did. So we created a vesting account, and when the vesting account was created, not only was the account that's holding the state for the vesting account created, but a Treasury token account was created as well. Because when we wrote our context data structure for creating the vesting account, we had two initializations. We had the initialization for the vesting accounts and the initialization for the token account for the Treasury. So this token account needs to be funded to be able to pass tokens from the token account over to the employee's token account later on in our tests. So since the SPL token mint was created with the employer as the mint authority, we're going to be able to mint tokens to the token account that was just created to fund it. So let's add that as the next step as our test. Should fund the Treasury token account. So let's define the amount that we want to fund. So this is going to be in Lamport. So we'll do 10,000 times 10 times 10 to the 9th. Okay. Now we can just execute the mint transaction. So we'll do mint tx await, and we're going to run mint 2. Okay. So we want to make sure that we import this, and we're going to update the import from the SPL token Bankrun. Okay. Now this has a few arguments. It's very similar to create mint. So first we want to pass through the Banks client. This is going to generate the same type error from create mint, so we can just copy over our little comment here. And now we have employer as the next argument, mint, and then the destination is going to be the Treasury token account. And we can just pull in the key that we derived earlier. And then the employer is going to be the signer. And then the amount is going to be the amount that we just specified above. Great, so now we can just console log that transaction. And let's run anchor test to make sure that went through. Okay, so you can see our whole test suite passed, which included 2 tests, and those both passed. So now our Treasury token account is funded. So we can move on to the next step. And this is going to be creating an employee vesting account. So now we can just define our transaction, and this is going to be the second instruction of our program. So we'll just name it tx2, and we're going to await. We'll call program.methods dot, and we'll do create employee account. Now this has several parameters to be passed through. So let's see. It has the start time, the end time, the total amount, and the cliff time. And because these are both I64 and U64, those convert to big numbers in TypeScript. So we're going to create a new big number, and we'll do, just for simplicity, we'll set the start time to 0 and the end time to 100. We'll set the cliff time also to 0 and the total amount to 100. So total amount is next, and then the cliff time to 0. This just helps us with testing because it sets the, so we don't have to wait for the cliff to pass. Okay. So now we'll just import bn from Anchor. Okay. So next is passing through the accounts. So accounts, and we'll need the beneficiary and the vesting account. Okay. And lastly, we'll send the transaction. So RPC, commitment confirmed. And we're also going to skip pre-flight to true. So there we go. So we'll console log this transaction, make sure it went through. Okay, and then we'll just confirm the employee account. So we'll just console log the employee account address. And this is going to have to be 2 base 58. Okay. Now we'll run anchor test one more time. Okay, so you can see the test suite passed, all 3 tests have passed, and it names each test. We can just go back to our console log to just check everything. So we have our first instruction, and it created the vesting account, and there's our transaction signature. We have creating an employee account, and here's the transaction signature. And then this console logs the employee account public key. And we also have the minting tokens to the Treasury token account. Now, the last thing we need to check is claiming tokens. So we'll make one more test. So should claim tokens. So now, because we need time to pass here to be able to claim the tokens, we're going to use a clock. So we're going to const current clock is equal to await, and from the bank's client, we can just get the clock. So bank's client dot get clock. Okay. And now we can set the clock in our context. So const dot set clock. And this will be a new clock with, and we're going to use the current clock slot. And then current clock epoch start time. spelled current clock wrong. Let's fix that. Okay. And then let's make sure we import clock. So this is an import from Solana Bankrun. Okay. And now we can see all of the arguments needed. So clock, start time, we need epoch next. So we'll do current clock.epoch. And then next is the leader schedule. So current clock dot leader schedule epoch. And then last is the Unix timestamp. So we'll just set this to 1000 in. Okay, now our clock's set. Now this is going to take a little bit longer in our Bankrun test, so we're just going to set a timeout. So we'll do await new promise. Resolve. Set timeout. Okay. Now lastly, we're going to run our third instruction of the smart contract. And here, we're actually going to use the second program because the signer for this instruction is going to be the beneficiary and not the employer. So methods, and we'll call claim tokens. Okay, so what we're passing through here is just the company name. Now we need to add the accounts. And for this, it'll just be the token program. And then we need the RPC commitment confirmed. Okay. And now we'll just console log our transaction. And this is our last test to run. So we'll run anchor test and see if the employee was able to claim their tokens. Okay, so you can see all 4 tests have passed, the full test suite has passed, and we can just look back at our console logs from the beginning of our Bankrun test. So we have the vesting account. When we're creating the vesting account, your transaction was logged. We have the minting to the Treasury token account. We're creating an employee account. Here's the employee account public key. And then here is our claim tokens transaction. Okay. So now that our tests have worked and we have our program built, we're going to be able to deploy our program. So in this whole bootcamp, we're going to be using our local testing environment. So let's get a local test validator running, and then we can deploy to it. So we're going to go back to our terminal, and let's just do Solana test validator. So running the Solana test validator just initializes a new test ledger and then is running a local validator on your computer. Now that this is loading, you can see that it is loading to my local host and we're able to now use it. So once you build a program, you're able to deploy. So we can just run anchor deploy, and we're going to specify the cluster that you want to deploy to. So we'll do provider.cluster. And this will be our localhost. Sorry, with Anchor, it's localnet. With Solana, it's localhost. Okay, there we go. So you can see it's deploying vesting. And you can see this is our program ID. Now, one thing to check is you want to make sure all of the program IDs are synced. So we're going to run anchor keys sync and make sure you're using the correct program ID throughout the entire workspace. Okay, so you can see all program ID declarations are synced. There was an incorrect public key in our anchor toml, so this was updated by running anchor key sync. So just because there was an incorrect program ID, we're just going to go back and rerun anchor deploy, make sure everything's correct throughout the workspace. Okay, great. We're going to start working on our front end. So we can take this program ID and connect it to our front end. So in the Create Solana DApp scaffold, there is one part that doesn't automatically update the program ID, and you have to manually update it. So we're going to go there and make sure that it's using the correct program ID. So that's here in our exports, and we actually need to fully update our exports because it's still working for our counter. So we're going to update our counter exports for our vesting program. So let's rename this to vesting exports. And what this is doing is it's exporting information needed to be able to pull into our web folder when we're creating our web app. Okay. Now everything that's counter we want to update. So this is actually our vesting IDL. And this is coming from idl.vesting.json. Okay. And we're going to import the vesting type from our target types vesting file. Okay. So now we can export our vesting and vesting IDL. Now we'll update the program ID for vesting. So vesting program ID. And this will be the vesting IDL. And now this public key should be the same as the program ID here. So we're just going to paste this in. Okay. And this will be the vesting program ID. Now we're going to go back into our files and just check for counter. Okay. Great. So you can see everything left with counter is in our React app. So we can worry about that as we're building out the front end. Now we can close out our Anchor file and open our web. Okay, so if you look on our web folder, we have the app folder, we have components, and we have public. We're going to start out in components. So you can see the components are separated between account, cluster, counter, dashboard, Solana, UI. What we're updating is the counter, because the counter is the area that's connected to the Anchor program. So let's rename this to vesting. Let's also rename this to vesting. Okay, just for consistency. Now you can see the vesting component is split into 3 sections. We have data access, we have feature, and we have UI. Let's first work with data access, because that's where we're going to be accessing all of the information needed to display on the UI. So we're going to import our get vesting program this time, and get vesting program ID. Okay. We'll just update everything from counter to vesting. Okay, so when you're using the vesting program, it's going to be making a query. And what we're going to want to set up is a query for the vesting accounts. So we're updating that. Now it's getting the program accounts based on the program ID. Now here's the initialization. We want to update this to initialize our new vesting accounts. So let's remove the initialization function. And this is just coming from the counter program. You had to initialize the counter program. So let's make this create vesting. Actually, let's keep this just to follow the same format, and we're just going to rename it. So we'll do create vesting account. Now this is program.methods, and it's going to be your create vesting account. This is going to pass through a company name and a mint address. So we have our company name, now this is a user input, and we're pulling this from the front end. And because we're doing that, we're going to have to tell this mutation that we're doing that. So we're going to update the mutation to have, we have a string, we have an error, and we also need to specify our arguments. So create vesting args, and let's write an interface to define what that is. So we'll do interface, create vesting args, and we'll need the company name. And we need this because this is a user input parameter, and we're using this as an argument for the create vesting instruction. And this is its string type. Now, another thing that we're going to have to pass through is the public key of the mint. And that's because we don't derive the mint account anywhere. So we need to pass through what the mint account is. And that is an account that's being used within the context data structure when you are actually creating the vesting account. But since it's being an input on the front end, we're going to make the type a string. And later when you're using the value, we're going to have to generate a public key from it. So we're passing through the arguments that we need. Our mutation key is going to be our vesting account creates. We're using the cluster. Okay, so here is where we want to pass through the company name and the mint. This is because these are the two arguments that we're grabbing from the front end and then passing through. So we just need to specify that. Okay. Now we can run program methods, and we're using create vesting account, and the only parameter that's being passed through there is the company name. Okay. And then the accounts that we need is going to be our mint account and the token program. So we'll go back to accounts, and we'll do the mint. And that is a new public key of the mint. And we're creating a new public key type because the mint is being passed through as a string type. And now we also need the token program. Okay. And then we'll just import the token program ID. And then we don't need a signer because we're going to actually be using the wallet that is connected to the front end of the application. So we'll just use the RPC, and then on success, it'll sign. And on error, it will give failed to create vesting account. Okay, great. So now we'll just update the return, and that is going to be create vesting account. Okay, so that's all the data we need for using the vesting program. Now we want to be able to use a vesting program account. So what this is going to be is once an employer has come to the front end and they have created a vesting program, now they can go in and update that vesting program by adding in employee accounts. So we'll go to use vesting program account. And this is passing through the accounts. Okay. Now we'll do use vesting program. And then the query is going to be for the vesting accounts. Okay, so now you can see we have close, decrement, increment, set. This is everything related to the counter. So we can just delete that. Okay, and we'll delete the corresponding returns. Okay, so now we're going to want to add in creating an employee vesting account. So this is going to be very similar to our instruction above. So what I'm going to do is just copy this over to make things easier. Okay. Now, instead of create vesting args, we're going to create an interface for create employee args because these are going to be different. When you're creating an employee account, you're specifying things like the start time and cliff time of your vested tokens. Okay, so interface, create employee args. Okay, now we'll define what that is. We need the start time, which is a number. We need the end time, which is also a number. The total amount, which is a number as well, and then the cliff time, which is also a number. So those are our 4 arguments needed when you're creating an employee account. Okay, so we can go back to our create employee vesting. We'll update this to employee account. And then we're passing through the arguments we just defined. So start time, end time, cliff time, and total amount. Okay, and then we'll update this to create employee accounts, and that is going to take in the start time, end time, total amount, and cliff time. Okay, and now the accounts. Let's go back to our Bankrun tests and just check to see what accounts we need. So accounts, test, Bankrun. So one good thing about testing in TypeScript when you're creating the front end, it's very similar, so it makes things a lot easier because you can always reference your tests and you know that these work. For creating an employee account, you need the beneficiary, and the vesting account. So we'll go back to the data access, and we're going to update our employee args to include the beneficiary, which is going to be a string because it's going to be a user input. Okay. And then we'll go back and do the same thing to convert it to a public key. So this will be beneficiary, new public key of the beneficiary. And we'll update that here. Okay. And now we don't need the token program, but we need the vesting account. And that is just the account. So now we can return the create employee vesting. Okay. Great. So for now, this is what we need for our data access. Let's update our UI and then the feature. So let's rename this to vesting UI. We need to update all of our imports. So let's just go through everything here. And we also need to update the data access file name. So we'll change this to vesting. And while we're here, we can update some of the unused imports. We no longer are using a key pair because we're connecting to the wallet rather than generating a key pair. And we're no longer using program. Okay. Okay, so we'll update the create to vesting create. And then we're using the create vesting accounts from use vesting program. Now, this is what the UI is going to look like. As of right now, it was just a button that you clicked for the counter. However, we need to accept some user input parameters. So we're going to have to change that a little bit. So first, we're going to need the company and the mint. So let's actually update this to have the company, and then set company, and we're going to use state. Okay, and we're just going to import this from React. And then we also need to do the same for mint. Okay, and now because we're using the wallet that's connected, we want to be able to get the public key from the wallet. So const public key, and this is going to be use wallet, and this should be an import from the Solana wallet adapter, and you can see that updated the import. Okay, so now we have that set up. Now we need to be able to get these two values from the UI. So let's create a text field for both of those. So in the return, we're actually going to create a div. And we'll put this button inside the div. Okay. So now we'll have a text field. So we'll do input. And let's just take what Copilot has, and we can update it as we need. So we have the type is a text, good. The placeholder is company name, good. The value is company. And then on change, we want to set company. Okay, great. Now let's also add in the class. So we'll do class name. And we're just going to define this as an input. And we want to have a border. We want the width to be full. And let's do max width for extra small. Okay. There we go. So that's our first input. Now we need another one for the mint. Okay, we're just going to accept what Copilot's suggesting and then review it. So we have the input type text, we have the placeholders, the mint address, the value is the mint, it's updating the mint on change, and then it's taking the same exact class name from above. Now let's update the button. Well, we can change the name of the button, and that'll be create new vesting account. Okay, now we're going to need to do a little bit different than how the counter is. And that's because we have some values that are being input, so we want to make sure that those are added from the user. So we're going to actually check the form. So let's do a few steps before we actually update the button. So first is we want to make sure that the form is valid. So let's do const, we'll do an is form valid check. And we just want to make sure the company dot length is greater than 0 and the mint length is greater than 0. Okay. Now we're just going to do a handle submit. So let's do const handle submit. And we're going to do if. So we want to make sure, 1, the wallet's connected, and 2, the forms are valid. So if the public key exists and if the form is valid, then it's going to run create vesting account. Dot mutate async. With the company name, which is the company, and the mint. Okay. And now we just want to do one more error handling, and that's just if the public key doesn't exist, we want to return an error to tell the user to connect their wallet. So we'll return connect your wallet. So now that those checks are in place, we can just update what happens on click for the button. So on click, all we're going to do is just handle submit. And then it should be disabled if the create vesting account is pending, and it should also be disabled if the form is not valid. So a user cannot click the button unless they've fully filled out both of the forms needed. Okay. And then we'll just update the button to have create vesting account is pending. And there we go. So now we've updated the vesting create page. Now we need to update the list. So what this does is it returns a list of all of the vesting accounts that are connected to the connected wallet's public key. So if I created multiple vesting accounts because I'm separating my company into separate mini companies and I want a vesting account program for each of those, it'll show all of them. We're going to update this to have use vesting program. And now what this is doing is it's checking the data of the program account. If the account is not found, it's going to return an error and say you need to make sure that the program account is deployed to the correct cluster, meaning if you're connected to LocalNet, the program should be deployed to LocalNet. If you're connected to DevNet, the program should be deployed to DevNet. So now you have the return and it has your cards. So this is going to be all of the cards associated with the vesting account. So we're just going to rename this to vesting card. And then we'll find where the counter card was originally written. Okay, and we're going to update this for vesting. So this should use vesting program. Sorry, this should be use vesting program accounts. And it takes in the accounts. And now we'll update this to have create employee vesting. Okay, so this we're going to make updates very similar to the previous section because we're going to be taking values from the front end and using that in processing our instructions. So let's set up all of the information that we need. We'll need the start time. And now instead of using state as a string, this is going to be a number. So we'll update that to a 0. And we'll do the same for end time, the same for total amount, and the same for cliff time. Okay. Now we're also passing through the company name, but because we're connected to the account, instead of needing to pass that through on the front end, we can just query the account because the company name is saved to the account state. So we're going to do const company name is equal to, and we'll do use memo. So we'll do an account query of the data in the account. We'll unwrap that and find the company name. Okay, and then we'll just need, there we go. Okay, so we can remove this because that's coming from the counter. And that was just querying the count from the counter state. So we're doing basically the same thing, but querying the company name instead. So now we'll return, we'll update the UI here. So we have, this is separating everything into cards. And we have the header. This is just querying the account. So from the account, instead of the count, we want the company name to be the header. Okay. Now, before the buttons, we're going to need a text input. So we're going to do basically the same thing we did above. So for simplicity, let's just copy that over instead of having to write it all out. Okay. So we'll make that update under the header and then under this div. So this div is separating all of our buttons. So we have an input. And this will be text. We're going to set this as start time. The value will be start time. And now we want the start time placeholder to show. So because of that, we're just going to do this. Okay. And now we have the value on change. It's going to set the start time. And this is going to be, because this is a number, we're going to have to parse the integer. So we'll do parse int. There we go. And we'll keep the class name the same. So now we're going to do the same thing for the rest of the inputs. So we'll just copy this and update this to end time. And this will be set end time. Okay. Then we'll do the same for cliff and total amount. So total amount comes first, actually. And we'll set total amount. And then we'll do cliff time. Okay, so let's just make sure we did all of that. So start time, set start time, end time, total amounts, and cliff time. Okay, and let's just write allocation here so it's easier on the front end so you know what that value is. It's the total allocation an employee gets. Okay, so now we can update our button. So the button, it'll have the same class. On click, we want to create employee vesting, and that is going to update these arguments to start time, end time, total amount, and cliff time. Okay, and then we'll update this to create employee vesting. Okay, and now we're getting an error, so let's figure out why. So you can see beneficiary is missing in the type. So we actually are forgetting one field. So let's update this to also have the beneficiary. So here we're going to need const beneficiary, set beneficiary, and beneficiary is a type string, so we're going to use the string. And then we're going to need to have an input field for that. And this will be a beneficiary. And this will be the wallet address. Okay. And we'll update this to just beneficiary. And this is not an integer, so we can get rid of the parse int. Okay. And then this should be set beneficiary. Okay. And now we can pass that through as well. Okay. And we'll update the name of the button to create employee vesting account. And this we can get rid of because this is coming from the counter program. And we'll just clean everything up. Okay, and we'll clean up our imports. Anything unused we'll get rid of. All right, so lastly we need to update our feature. So the counter feature is going to use the vesting program, it's going to use the vesting create. Let's update our counter list to be named vesting list. Okay. Then we'll update everything for vesting. So this should be a vesting feature. Okay, this should be vesting create and vesting list. Okay. We'll update the title to vesting smart contracts. Actually, we'll just name it token vesting. Okay. And then create a new vesting account. Below. And we'll just remove the rest of these comments. Okay. So let's see. This is our feature. We're setting up the vesting feature. We're connecting the public key from the wallet that is connected to the front end. We have the program ID from our vesting program. If there's a public key connected, it'll return to create a token vesting account. Okay, so this looks like everything we need. We're just going to rename this vesting. And now we should have gotten rid of almost everything related to the counter by now. There's just one more thing we're going to need to update. So vesting, let's just Command-Shift-F for counter. Okay, these are all just comments. So here we go. In the layout, we'll update this to vesting program. And this should be using the vesting path. On the page, we want to use the vesting feature. And we're going to import the vesting feature. Okay. These are all comments. Okay. And now let's just update our queries to vesting. Okay, so now we're good to go. So now to recap everything that we've done so far, we've created our smart contract using Anchor in our Anchor workspace. We've built the project and deployed it also using Anchor. We deployed onto our local host, so we're running a Solana test validator locally on our computer. And then we've updated the front end to be able to connect to our wallet and execute smart contract instructions. Now that all of that's done, we're going to run on our local host, the UI, and be able to test it out. One thing to know before we start running, you're going to want to make sure that your package.json, the lock file, is updated because it's probably still going to have dependencies linking to all of your counter files. So I would just delete the package.lock and rerun npm install to make sure that everything is set and good to go. And then we can just go into our web folder. So we'll cd into web, and we can run npm run dev and get this running on our local host. Okay, so we're gonna open up our browser, navigate to our local host. Okay, so this is what our UI looks like using the Create Solana D app. You have the cluster that you're connected to. You can see here we're connected to local. You have your wallet connection here. And this is connected to my Phantom wallet that I have linked on this webpage. Now, you can see that it automatically prompts you that I'm on local, but I don't have an account found. So I'm going to request an airdrop. So this account that my wallet is connected to is now funded with Sol, and the account exists. So this is our placeholder. You have this basic front end that has just GM. This is your new Solana D app and some links. Now, what we updated was the vesting program tab. And just to make sure you're familiar with the Create Solana dApp scaffold, we'll just go through all the other tabs first. So you have this account tab. And this shows the account that I have connected. Here's my wallet address. It is the same as the wallet that's connected. You can see that I have one Sol that I just airdropped to myself. You can see the transaction history, which was the Sol that I just airdropped to myself. You can see that I have no token accounts currently. And you can see that we have the option to airdrop, send, and receive funds from my wallet. Now we can move on to the clusters tab. And these are all the clusters that you can connect to from your front end. So you have DevNet, you have LocalNet, and you have testnet. Currently, we're connected to local, and we're running our local on our Solana test validator in our terminal. You can see our status of our current validator. Here's the process slot, confirm slot, finalized slot, and full snapshot slot. So you can see everything's running correctly on our local host. All right, so now we can go to our vesting program. You have the name, token vesting. It says create a new vesting account. This is the program ID of the account that we just deployed. Now let's test this out, but we're going to need an correct mint address for this to work. So we're going to go back to our terminal, open a new tab, and we're going to create a mint on our localhost. So let's do SPO token, creates token. I'm going to specify the URL to be your local host. Okay, so you can see we're creating a token under the token keg program, so it's an SPL token. Here's the address of the token we just created, and there's the signature, so you know it was a successful transaction. So we're going to copy that address, go back to our UI, and paste the mint address in the mint address field. Okay. Now we'll do the company name, so we'll just name this bootcamp. Okay, so we'll create a vesting account, unlock, confirm the transaction. Oh. Great, so now you can see the new vesting account that was created for the bootcamp. And this allows the employer to now come in because this bootcamp card from the new vesting account that was created is connected to the public key that I'm connected to on the UI. So all of the vested accounts that I create are going to show up here, and then me as the employer is able to come in and create employee vesting accounts for employees for each account that I create. So if I wanted to make another one, just like a subset of vested tokens, and I set this as my 2024 bootcamp employees. We're going to just create new vesting account, confirm. And now you can see this is my other set of vested allocated tokens. Sorry. You can see this is my other set of vested tokens. So now I'm managing two different accounts that have separate tokens. I could create a separate mint address if I wanted to, so we can actually just test that out. I'll go back to the UI. I'm going to run SPL token create token. Now I have a whole new token. So let's say I wanted to have some employees vested with one token and some with another. I can do that. And we can do just a test here, create a new account, confirm. And now you can see here's my next account. So this is related to one token, and this has a mint address of another. So now I can keep track of all of the vesting accounts that I create, and within those, I'm now able to create employee vesting accounts that have a start time, total allocation, end time, cliff time, and the wallet that I want the beneficiary of this account to be able to claim tokens. So there's my UI, and you can see everything works with the program that we created. And overall, we created a Smart contracts, we tested it using Bankrun. We updated the front end with our Create Solana DApp scaffold, and we tested it on the front end. We also deployed our smart contract to our local host while we're running our Solana test validator locally. So there's our token vesting DApp.